first seminar of 2023. It's a great pleasure to welcome here Stefano Soatto, a professor, has been for over 20 years at UCLA, and also for the past few years at Amazon, AWS. Previously he was in Washington University, and before that took a PhD in Caltech. Stefano's interests are in computer vision and nonlinear estimation and control theory, in particular ways for computers to use sensory information to interact with humans and the environment. Stefano is a recipient of several prizes, the David Marr Prize, also the Siemens Prize, the NSF Career Award, and the list goes on and on. So please join me in welcoming Stefano, who will...
Thank you. It's a great pleasure to be here. This is the first live talk I give since the pandemic. So hopefully that will work with the audience. So it's certainly been a couple of interesting years, both in terms of sociology, politics, and science. Certainly it's never been the case during my lifetime when things that we do in research impact the world so broadly and so quickly. And so I will talk about some questions that have obsessed me over the past couple of years as I've seen developments progress in deep neural networks and capabilities that emerge. And these are questions that have traditionally been the purview of maybe philosophers, maybe people who were worried about the foundations of math, but have rarely kind of resurfaced in engineering, but now they are becoming real in the sense they impact real material decisions, whether you trust authentication systems, whether you believe and want to bet on the metaverse and things like that. Right? So I will ask questions that may seem vague and philosophical, but they really stem from real engineering problems that I've been witnessing over the past couple of years. Questions, I'm summarizing this as with can a neural network understand what's real? So obviously we need to say what understand meaning, what real means. And I think you agree what a neural network is, but I actually will often refer to a neural network as you. So because at some level of generality, some of the considerations apply. But you know, how many of you have played with ChatGPT? How many of you have not played with ChatGPT? Okay, so how many of those who have not played with ChatGPT are in CS? Okay, I will not take note of me. So can it reason? So you read, oh, it's reasoning and so on. Does it reason? And how many of you have heard of NERSC? Fewer, okay. I'll say briefly what it is, but the word on the street is that they somehow capture reality, whatever that means. You know, we hear a lot about neural networks kind of understanding the physical world. What does it mean, and do they do it? So these are seemingly vague, but questions that date back to issues that people were dealing with at the turn of the previous century and then have gone dormant since, but now they are real in the sense they impact the real world. So I will use words initially informally and then try to formalize them, words like understanding, meaning, knowledge, and information in increasing order of precision. But I will start with data because data is the one thing I hope we all agree with. Data is whatever sits in the memory of your computer. You can touch it, you can see it, you can store it, you can manipulate it. Okay, but even as we go to information, things get a little bit tricky. So I want to give you a flavor of some of the technical issues that arise when you reason, when you talk about information in the context of trained deep learning models. And so I'll spend a little bit of time on the notion of information, and then I will try to get to knowledge and meaning, building on that. And the second part will be, and I will do a little experiment on you since this is in person, since all of you are real, at least I think so. And we'll see if that works. Okay, so what is information? So many of you use the term informally. Many of you may have taken a course in information theory. Information, the way we use the word technically, dates back to the 50s, to communication engineering, where there's a notion of a channel and a source, and data gets transmitted, and there are frequencies, and there are distributions, and there's entropy. So entropy is a measure of uncertainty or volume of a distribution. But when you train a network, you're given a data set. So whatever information about the task you're trying to learn means that information is in that data set. It's not in a distribution of data set, it's in that data set that sits in the memory of your computer. You have one of them, typically. So, technically speaking, the entropy of that is zero. The distribution over the space of data set of that one singleton data set is zero. Okay, you could say, well, but this data set, I could shard it in a different way and think of it as a distribution. If you do that, then once you train the model, whatever information means that was in the data set, because there was nothing else before you started training, is now in the weights of the trained model because there's nothing else left after training. But after you're done training, you have one set of weights. You don't have a distribution of weights. So again, the entropy of that is zero. And even if you think in terms of mutual information, for those of you who are familiar with that, or even differential mutual information, if you think of the trained network as a function, it's a deterministic function. So it has infinite mutual information, differential mutual information. So these notions really are challenged by deep learning. Okay, so now you can hand wave it, or you can try to make it precise, but then when you get to numbers, try to compute numbers, these numbers, it's not clear what they mean. They don't make any sense. So this is just to say that there are issues with traditional notion of information as they pertain to deep learning. So you could say that in the language of Shannon, a trained network contains no information, which obviously doesn't make any sense, so something is off there. Meaning is even worse. Okay, so if you try to get people to tell you what does meaning mean, what is semantics. So in order for you to talk about meaning, you need to have a language. And language is what gives meaning to data. And different disciplines assume different language, whether it's and associated to that there are different concepts. You might have heard words about grounding, agency, intentionality, relevance, complexity, value, and so on. So, but really when we talk about language, the question is, what is the entity that imposes the language? Okay, is it the designer of the model that we're training? Right. So you speak a language, you have a natural language, you impose it when you decide on the loss function, the regularizer, and so on. Or is it in the trained model? Once you're done training, maybe the model has developed an inner language. It's not your language, it's its language. Or is it maybe in the data that you use to train the model? Or maybe it's in the environment that generated the data that you use to train the model. Right? So all of these are viable options, and it's not clear which one is the right one, if there exists one, and how that language comes into being. By the way, feel free to interrupt me at any point. This is the beauty of in-person. So if I say something that doesn't make sense, or you think it's wrong, or offends you, please interrupt me anytime. So I just want to give you a cartoon of what semantics means today when we trained large-scale deep networks. So you have some test data, and you attribute meaning to that. You could say, or you, as in the trained network, okay, could say, well, this is an astronaut riding a horse on the moon. And how can you possibly do that? Well, because this image, which you've never seen before, some piece of it, you don't know which one, has some property, you don't know which one, that has something in common, you don't know what, with some other data, you don't know what data, that some annotator, you don't know who, attached the label astronaut riding a horse on the moon. Okay, so you can see that the link, first of all, the language here that allows you to attach meaning to your image is inside the head of the annotator. It's not in the pixel, it's not in the world, it's not in the objects, it's not in the trained model, it is in the head of the annotator. Okay? And so you're really relying on a very tenuous link between the data, which is objective, and this meaning that you attribute to that through a very long induction chain over which you have no handle on veracity, falsifiability, objectivity, uncertainty quantification, anything like that. Okay? And when you rely on what's on people's head in order to attach meaning to things, there are things that can go wrong, and that do go wrong. So, do you see, I mean, some people see Jesus Christ appearing in their bathroom on Monday. Are you going to argue that that's wrong? This is what they see, right? Is there a way to say that this is not true? So this phenomenon is well known. It's called pareidolia. I'm told that if people go deer hunting during the weekend, when they go back to the office, they see deers everywhere, right? So make sure that if you go deer hunting, you don't bring a gun to the office. But essentially, this is what we are relying on today when we do large-scale supervised classification in order to attribute meaning to data. It's a very weak term. So if you try to make the word meaning precise, you have to define the language. What language is the one that attributes meaning? And here's where things get tricky. So I'm going to give you a very cartoonish, naive taxonomy of the various philosophies that people assume in order to attribute meaning to data. So the one that we as engineers adopt almost without question is the one where you assume that there exists a world out there that generates data. Data is objective. And then you pick a task, okay? Usually it's defined through the data, right? The training set defines the task. With that, you train a model or a representation which is a function of the data that also depends on the task. And you, as the designer, are the one who imposes the language. You impose it through the choice of loss, of risk. You impose it through the choice of architecture, inductive biases in the model, through the choice of the regularizers or priors, through the optimization procedure imposed, or even through the choice of data that you want to select in order to get the answer you want. Okay, so here, the language is the one of the designer of the trained model, and this is called naive objectivism. So objectivism because this appears to be objective. Yes, of course there exists a world out there that we share, we're all in this room, and of course that generates data, right? And then once we train a model, we define a notion of optimality, and so long as I can solve the problem optimally in the sense of some generalization bound or risk, that's great. Objectively, I'm better than anybody else. But now you come with a different loss, and now you're optimal with respect to that. Who's right? There's absolutely no way of saying. There's no comparison. And this is why this is called naive. And Jan Kundering summarizes it eloquently. It says that the Marion account refers to this as the account from David Marr, but this is basically, it's called, it's just called naive objectivism. Requires magic to work as advertised because you are the one who chooses the criterion, all the inductive biases for the architecture, loss function, regularizers, and so on. And so there is really no way for you to say that that is the right choice. Okay? So there's no objectivity in this framework, and that's why it's called naive objectivism. Okay? Make sense? Okay. Now, you could pretend to make this objective. The Bayesian risk has some sort of objectivity, but of course there you have to choose the prior. So Kundering objects strongly to the notion of objectivity of Bayesian inference. You could try to make that a little more objective by saying, well, we don't know where the data comes from, so we don't want to assume that the world exists and whatnot, which is something that we engineers don't particularly bother to, but philosophers are very, very troubled by. And then you can try to make the data the task. Okay? So your task is to create or predict or interpolate or extrapolate the data. And this is what we do most of the time these days. Mass data encoding, prediction, all the type of unsupervised, semi-supervised, self-supervised, or predictive loss functions that we use to train the large-scale models that we have fine-tuned other things. Okay. So this is also in the sphere of naive objectivism because you are the one who define the loss, the predicted loss, and also it kind of gives up on the notion of semantics because if your goal is to recreate the data, there's no objects in data. There's pixels, there's bits, so there's no analysis. You don't need to break the data into pieces and define symbols and define relations. There's no language in data. Okay? So a completely different approach is one where, represented by Gibson, where he says the language is not yours, of the designer of the model. The language is the language of the environment. Okay? The environment speaks a language because of the various ecological statistics, the fact that there are discrete objects that stick out of the ground and so on. So the task is really interacting with the environment. The word Gibson uses to resonate with the environment. I'm not sure what that means, but you get the picture. And this is called naive realism. Naive, again, realism because it's the real world out there that imposes the language on us. Why is it naive? Well, first of all, you have to assume that there is a real world, which, okay, again, philosophers fret about that, we don't. But even if you and I share the same world and observe it, we end up with representations that are completely different. There's no link that can be established between how you encode and represent the world in your brain and how do I mine, or how two different networks trained on the same data can exchange information about their weights. There's no objective connection between these. So, and this is, but there's merit, in my view, to this approach. So I've been trying to pursue it since 2005. Some results since 2009, so far unsuccessful, and lots of people have tried, most unsuccessfully. According to Tadeusz, even Gibson was not a true Gibsonian. So if you want to do this right, it's not easy. Finally, the last one, which is the one that's considered to be completely unpalatable from the scientific point of view, even though it is the one that originated from the logicians and the foundation mathematicians in the late 1800s, early 1900s. It's called idealism, so Frege, Russell, Wittgenstein, Descartes, and so on, where you're saying there's no real world. The real world may or may not exist. We may be in a simulation. Who cares, right? We know there's data, and we know that we have some type of computational power in our brain to not represent, because there's nothing there to represent, but to present, to hallucinate data. And then the world gives us feedback, or mainly the data gives us feedback about how this data fits, and that is what we use to update our own representation. Okay? Everything exists inside your head. You don't need to worry about whether the world exists. And this is obviously very unpalatable scientifically because it's totally subjective. I have my own world, Pierre has his own, Charles has his own, and you can imagine the babble, the confusion of things. So, but this is the point of view of analytic philosophy, and this is what Kudrin refers to as the Goethean account. I prefer to refer it as the Cartesian account, which is widely considered unscientific because it's entirely subjective, yet it's the only one that does not require strong postulates in order to build a theory on it. Okay? So, which one is right? Well, Shannon didn't care. Turing said, it's about falsifiability and imitation game. Marr said it's about inference. Gibson said it's about interaction. Descartes is about cogitation. Hilbert is about deduction. Kolmogorov is about complex computation. I'll add one philosopher that I am tied to who says, well, the way we measure meaning is in terms of value. And that has some objectivity. For instance, even whether or not these models have meanings, people do use them, and do use them to accomplish tasks well enough that some people are willing to pay money for it, which is something that never before happened in AI at scale until just, let's say, a decade ago. Okay. Even expert systems of the 80s and 90s, yet some people were paying for it, but not enough to pay for it. So now there are services that literally tens of thousands of people access to and use to solve everyday tasks. Okay? So from that perspective, it's already been a success. Okay, so we can be proud as a community and stand on the shoulder of people who persevered through the various winters and gave us the tool that allow us to do this. There are red flags. Okay, so The first I would mention is that now there's a lot of excitement on large language models. So the language is human language, which is manifest in corpora of text that we harvest on the web. And you train a model with masked autoencoding of text, and then you do all sorts of things with it. Okay, but unlike the physical world, which is what I would like to for our systems to understand, which has arguably infinite capacity, physicists might disagree, but it's objective that human language is a human construct. Its complexity is finite, no bigger than the human brain. Human brain has a few tens of billions of synapses. And some people argue that the amount of information that humans store in the process of language acquisition is tiny, 1.5 megabytes, fits in a floppy disk for those old enough to remember. So how come we're training hundreds of trillions of parameter models to capture something that should fit in 1.5 megabytes? Okay, at most 1.5 megabytes. So there's something there that tells you, well, maybe the red flag that I'm most interested in is one where the imitation game has essentially been won, not only in text. You play with ChatGPT. I was surprised a couple of years ago when I was in a chat with customer service, and it took me 5 minutes before realizing, wait, I'm talking to a bot. And it took me 5 minutes to realize that, and that time will get longer and longer. And Turing said, we'll have cleared the imitation game when we can we get it wrong 70% of the time, but GPT-3 scores in the 93rd percentile on the SAT verbal. So we're done. But even images, static images, they're images you cannot really tell if they're real or not. And my question is, what exactly does that mean? And that will be the topic of this today. So what I would like to really be able to say something, either positive or negative, is that can a deep network tell me, for instance, if the person who's showing up at the door or the person who I'm talking to on Zoom is a real person? Okay, maybe I spent the past 2 years talking to bots. So, I will now get into some more details, but I want to open for a few questions now. So I will talk a little bit about information with some technical jargon, just to give you a sense of the ground from which we start. Because for me, information is manifest in a set of fixed data that sits in the memory, whether it's weights or data sets, not in some distributions that exist, but you only get samples of. And then I'll use that to talk about knowledge. Okay. Are there any questions so far? So I gave a very broad overview of kind of various positions with respect to these issues in various communities. Any questions? Objections? Okay. All right, so I'll talk about information, because for me, so information comes from data, knowledge comes from information, understanding comes from knowledge, and so there's a sequence that I want to follow. Okay, so as I said, if you are trying to train a model for a particular task, then all the information about the task that the model knows is in the data set. That's how you instantiate or specify the task to the model. And after you're done learning, whatever information was in the training set is now in the weights of the trained network. There's nothing left, nothing else left, right? So, and how do you use that information? Well, you take some test data that never seen before by design, you pass it through the network, you get some activation. Those are a function of the data set, so presumably they use some of that information. And then to know how well you're doing, so put a value, a number to that, you measure how different they are. That would be your test error. Of course, you cannot do that until you have the test data. Okay, so in a sense, you only know how good you were until it's too late. So, and there is an industry that tries to predict how well you will do on data you've never seen. And this is generalization bound. And if you look at this generalization bound, many of the ones currently in use look like this. They look like, do we have my mouse? I don't have my mouse. Okay, they look like, on the left-hand side, you have the training loss, which is what you measure. It's a function of your data set. You can do whatever you want to it. You can minimize it. You can tweak it. So that's under your control on the left-hand side. On the right-hand side is the test loss. Sorry, on the left-hand side, I'm standing backwards. So On the right-hand side, you have the training loss, which you have control over. On the left-hand side, you have the test loss, which is what you would like to keep small, but you cannot compute it. So you would like to bound it with something on the right-hand side which you can measure. That would be requirement number one. And number two, that is less than infinity, because otherwise you don't get something very useful. So, and typically on the right-hand side, you get something that looks like you get the training loss plus some functions of the mutual information between the weights and the data set. Okay? So if you're not familiar with the notion of mutual information, use the intuitive notion that that measure, it's presumably a number, that measure how much information is exchanged between the data sets and the weights. Now, not really between the data set you have and the weight you train, but between the distribution from which the data set was drawn, which you have no clue of, and the weights, the distribution of weights that you could have converged to, but you just picked one. Okay. So the point is, on the right-hand side, it's a quantity that you don't have a number for, you don't measure it. Okay. So part of the challenge is, but nevertheless, you find theorems with bounds for that, and the question is, what do that mean? So I'll focus on this quantity. And one thing to note, by the way, is that you would like to think of the neural networks having a lot of information about the data set, as much as they can, right? But in fact, this is saying that you want as little information about the data set as possible. So you want the weights to forget as much as possible about the data, so long as they can keep the training loss small. Okay? So in a sense, to learn, you need to forget, which is, I love that, because as an aging professor in my 50s, if I forget things, I tell my wife that I'm still learning, so that. So some people do compute numbers here. I'm one of them, and Roy certainly and others have done that. So technically speaking, if you wanted to do that, this is what you would need to do. You would need to get a bunch of different data sets. On each of them, you train a model, you get a bunch of different weights. Okay? Now you take these weights and now you average the results over all possible data sets, and you get the posterior, or what's called the adapted prior P of W. Okay? And now the Kullback-Leibler divergence on average over data sets between the posterior on the weights and the prior on the weights tells you the mutual information, which is a number. Okay? So you would have to compute this number, you would have to realistically average over all possible data sets in the world. Obviously, it's not great, but from every possible data set in the world to one, there's a lot of room in between. So most of these bounds are vacuous. Not only, but even if you could compute this number, okay, I'm going to try to convince you that that number doesn't have any meaning whatsoever when it comes to generalization. Okay? So here's the experiment, the thought experiment you do. So take the weights that your model has converged to. Okay? They're sitting in memory, you can see them, you know what they are. You also have the data set. So take every single datum in the data set and you append it to every single weight. You typically have more weights than data points, so you can do that. So you basically take your weights and increase their bit rate, increase their storage by the volume of the data set. Okay, you do that for all the data set. Okay, so the mutual information between the weights and the data set has increased. Obviously, you store the data set in the weights. In fact, it's maximum. Okay. Do you expect that your model would work any better? Probably not, right? Because first of all, the data set is after the least significant bit, but also because whatever information about the task was in the data set was already extracted in the weights, and so now repeating the data set, which you will never see again, right, by construction, will not help the model generalize better in any way, shape, or form. So you added mutual information, but you didn't improve generalization. Okay, so that tells you that this measure of information is really not the right one, even if you could compute it, which you can't anyway. Okay, so what is the right measure of information that you should use? Okay, so in information theory, there's a saying that if Shannon hasn't said it, it's not real, it doesn't exist. So not surprisingly, Shannon said something similar in the 50s, when 1950 in fact, when he tried to measure the entropy of the English language. And the way he did it is pretty much the way we train these models. You know, take a page of text and perturb a word or a character by either removing it or misspelling it or switching the order, whatever it is. If at the destination you can reconstruct the message exactly as it was, then obviously that word that you altered doesn't contain a lot of information. You can throw it away, replace it with noise, or replace it with blank, and nothing will happen. Okay. On the other hand, if there is a word that if you remove it, it completely changes the interpretation, or you have no clue what that word might have been, that requires a lot of bits to store, and you want to allocate a lot of bits to store that. That contains a lot of information. Okay. Now, in language, this is easy because the data is language, the task is language, the representation is language. You're all in a closed system where everything fits. In vision, this is not the case. Okay, so you need to do a little bit more work. Okay, and the way to work is as follows. So the main difference here is that the amount of information that the weights contain depend on the level of accuracy that you want to get out of your model. Okay, it's not one number. Okay, it's a whole Pareto frontier. So let's say that your task is to distinguish airplanes from cartoon characters. Okay, and you want to do that, and I ask you, okay, how much information do I need? Okay, well, I'll tell you, what performance do you want? You know, if you want 50%, great. You need 0 bits. Every time an image comes, say cartoon characters, and you're wrong 50% of the time. That's good enough. Everybody's happy, right? Okay, I said, no, wait, that's not a good one. How about 75%? Okay, for 75%, I'll store a color histogram. If there's a lot of blue, I'll say it's a plane. If there's not a lot of blue, I'll say it's a cartoon characters, and probably I get it right 75% of the time. But if I want, and by the way, now I can play Shannon's game. I can say if I perturb my data, right, or which is equivalent, if I perturb the decision boundary, these are dual in the first layer, my error rate stays within the bound that I prescribed, so 75% correct or 25% error. Okay? But if I now want 99.9% correct, now I have to account for the possibility that there may be planes that look like cartoon characters. So as soon as I perturb, and there are maybe planes that have no blue, as soon as I perturb the boundary, now I'm going to start making a lot of errors. And so now I need a representation that's much more sophisticated. I need a lot more information encoded in the weights. Does it make sense intuitively? Okay. So if you operationalize that, what you get is the following. Take your data set, one data set, the one you have. Not a distributional data set, the one you have. Okay. Train a model, however you want to train it. Stochastic gradient descent, deterministic gradient descent, whatever. Doesn't matter. You arrive at one data set. Not a distribution of weights, one set of weights. Okay? Now, this set of weights, W0, perturb them. How? You choose. Add noise. Add noise, whatever kind of noise you want. Okay, you like Gaussian, now you like Bernoulli, add Bernoulli, whatever you want. That's your measurement device, that's your unit. Okay, you pick the device, you like inches, meters, whatever. So you perturb that, and then until the training loss, which you measure, that's a number, right, stays within your prescribed tolerance, okay? Say 0.1% error, right? So I'm going to add noise to the weights until my training loss reaches that error. At that point, I'm going to look at the noise I've added. I chose it, so I know exactly what distribution it comes from, okay? I compute the entropy of that, which is now well defined. That's a number, okay? That is the information that the weights contain that is redundant. It doesn't have any effect on the training loss. Right? You probably have seen this when you train deep networks. You have all these weights, and there are some weights that you can change however you want, and nothing happens. Okay? That noise in that direction, right, tells you how much information is redundant or inaccessible because the model doesn't see it. You do that for all your millions of directions. You get, a distribution. You compute the entropy of that. That's your number. That's the redundant information. Now, whatever information was there to begin with, if you subtract from that the redundant information, is the residual or the accessible information. That's the information that the model has access to, that it can use for future data to answer your queries. Okay? Make sense? Questions? Okay, so to define information, you have to solve this optimization problem, which looks daunting, where you have some knobs which look like a bug, but it's really a feature. One is you have to choose the performance level you want, tau. Okay? The less performance you want, the least information you need. Two, you need to choose the distribution from which you perturb the noise. Again, that's your choice of units. But once you've done that, this is a well-posed definition that doesn't depend on what kind of network you have, how you train it, and so on and so forth. So that's what we propose is should be used in order to measure a generalization. If you take this constraint optimization problem, write it in Lagrangian form, and look at the second order approximation, you don't actually need to technically add noise, right? Because you can compute entropy of Gaussians in closed form. You get the Fisher information of the weights of the trained model, which is nice that you get that connection. Okay, so the log determinant of the Fisher is the information in the weights. This is the Fisher around the trained point, not around the initial condition like in NTK, for those of you who are familiar with neuron tangent kernel. That has no meaning in this context. Okay. Okay, so now if you take that and write it in Lagrangian form, as I said, you get an expression that will look familiar to some of you are familiar with information bottleneck. It is an information bottleneck. It is a training loss, typically an empirical gross entropy, and a mutual information term. But now it's a mutual information term that you can compute. Okay? This is not the same information bottleneck that Tali analyzed and Roy, where they look at the information bottleneck between the test data and the activations, okay, which is your statement of desire. This is between the data set and the trained network, okay, which are all deterministic. Okay? So in the pack-based bound, we propose to replace the mutual information with this accessible or actionable information. Okay? And you get, not only you get a variational principle associated with the definition, meaning that if you minimize that object there, which is called the information Lagrangian, you are guaranteed optimal generalization, even though you don't know the exact number because there are constants. You don't care. What you know is that if you manage to minimize that, that's the best you can do. Okay? So that's the value of the pack-based bound, not as a number that tells you about generalization, for that you do cross-validation, but as an inductive principle, as a variational principle that tells you what is the right quantity that you should optimize if you want maximum generalization, and that quantity is the actionable information in the weights, or accessible information in the weights. Okay? Okay, so now we have a way of computing, defining and computing information, not in a distribution, but in a trained network. Okay? Not just technicalities there that are not insignificant. Okay, so now the question is, where's the language here? Where's the meaning? There's no language here. So once you've done this, as I said, whatever information or knowledge was in the data set, now it's in the weights. So if the trained model has a language or develops a language or a language emerges, it's in the weights of the trained model. There is nothing else, right? Okay, so does a language emerge? What does that mean? Okay, so do neural networks develop an inner language? Do they have symbols, relations, deduction, and so on and so forth? Okay, can we say something about that? If they do, can we translate from that language, call it neuralese, to our language so we can talk to it? Okay. Or if they don't, then are they just, a dumb data torturing device that all it does is it harvests whatever structure is in the data, but doesn't have any awareness of that? It just co-opts the language in the data. but it's completely unaware of content, meaning, and incapable of any form of deduction. It can give you the appearance of reasoning, but not in any meaningful way reason. Okay? So these are the questions that I'm going to move on to next. Okay. Okay. So this is, you consider this as part one, and if stuff was unclear to you, went over your head, the take-home message from there is that it's clear what the data is. Okay, there's no disagreement on that. Information is a tricky concept for trained networks, but we have ways of defining it and computing it for trained networks that captures the fact that if a network has maximal information, it also has maximum generalization, okay? Which is not true for Shannon's information, okay? Okay, so just a reminder of what semantics means today. It means that there's some meaning or semantics, some attributes that some entity, the designer, the annotator, whoever that is, imposes on data which are a manifestation of reality. It's not reality, it's manifestation of reality. That's mediated by language, and language requires induction. So in order to say this is a astronaut riding a horse on the moon, there needs to be a chain, okay, that connects to the brain of the annotator. That language is not in the data. There's nothing in the pixel here that says astronaut, right? It's not in the architecture. It's not in the environment, because this environment does not exist, right? It's really inside the brain of the designer. Or, if you are a trained network, as we just said, that language, if it exists, has to be in the weights of the trained model, okay? Now, whatever that language is that represents the data that you use for training is an abstract concept. It's something that exists in intrinsically finite representation, whether it's inside your brain or the weights of a trained network, okay? It cannot capture the continuum and infinity. Right? So the question I would like to ask is, does a deep network develop an internal language? Okay? And if it does this language afford deductive capability? Can it reason? Okay? If it can reason, can it be used to discriminate something which is real, okay, that intuitively you think, well, the physical world is real, as can a network say that? And if it does have an internal language, can we transplant that language? Can we translate that language? Now you can see my interest in this because as a father and a professor, I would like to transplant what I've learned onto the brain of my kids and my students. Why should they go back to kindergarten? If you think about the evolution of knowledge through the course of evolutionary history, we spend our life learning, then we die, that's all gone, other than what you have managed somehow, despite all the noise, to transmit to your kids through your DNA, which is a very, very narrow channel, and whatever you taught them, and to your students. But it's an extremely inefficient way. So why can I just not transplant what I've learned? And if you are two neural networks, if this one learned something, why can I just not copy it over? Okay. So can I transplant knowledge by bypassing the medium? Okay. Okay. So I'm going to make some claims that we've proven, but I'm going to try to give you an empirical proof through a little experiment here, if you're okay with it. Okay. So here's the experiment. So I have an abstract concept in my brain, something that I've learned, okay? It resides inside my brain in whatever language my brain uses, okay? Which is not natural language. There's no, English words inside my brain, okay? You may or may not have some related concept, but I want to transfer what's inside my brain inside yours, okay? So the way I'm going to try to do it is, I have a concept in my brain that I can use to generate some data. I'm going to show you some data, and then I want you to tell me when you believe you know what's inside my head. Okay? So I'm going to show you some data. This data is going to be in the form of pixels, so you're going to see pixels, you're going to elicit responses to your cones and rods, and that will somehow be translated into spikes into your brain, whatever happens inside your brain, I don't know, at some point you get it, okay? Once you get it, you let me know. And how can you let me know? Well, you're gonna use sound to communicate with me. Okay, so this is a 10-second experiment, okay? So the way you communicate with me is you start, when I start the experiment, you start with oh, as in oh, I have no idea, okay? Oh, when you get it, okay, you flip to E, okay? But don't stop. Don't stop when you get it. 10 seconds, just keep going, okay? All right? Okay, are you ready? Yeah? I want everybody, don't be shy. So I'm collecting data here because it's the first time I do it. Okay, keep going for 10 seconds. Okay, ready? 3, 2, 1. Okay. 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 So what's going on here? Okay. So clearly, I certainly have the concept of pi in my head. Okay. Pi is an abstract concept. It doesn't exist in reality, right? Nobody has ever seen all the decimals of pi. Not possible, right? But I have a finite representation of pi in the sense that you tell me, give me the 1 millionth decimal, I have a procedure that will tell you, and it will be right. Give me the 1 billionth, and I will be right, and I can give you whatever decimal you want. So that I can generate the infinite efflux that the concept can generate, right? So you agree with that statement, right? It's an abstract concept, has infinite possible manifestations, but I can get it. Not, well, sort of get it. No, I can get it, exactly. I understand pi, right? Okay. Now, you also can understand pi, I assume, right? Now, at some point you thought you understood that I was thinking of pi, right? And you were convinced because all I heard was E at some point, right? But then at some point you say, wait a minute, no, something is off here. I thought I understood, but I didn't. And I know for sure I didn't, because I know for sure this is not pi. Okay? So there's quite a bit in that. So I'm going to try to formalize what came out of this little experiment. Okay? And then at some point you might understand, okay, well, he was trying to fool us by playing this experiment. This is what probably Pierre got it, but at the answer, I see what you're trying to get to here. Okay? So what does it have to do with reality? I started by saying I want to understand if a network can say what's real. Okay, so what is that? Pi is an abstract concept. It's a symbol, you know. Well, bad news is that the physical world, as we experience it, is an abstract concept. Okay, whatever you know about the physical world, you only know through the mediation of your sensors, which are finite. You have finite data accumulated in finite time, processed with finite capacity, and stored in finite memory. So the representation of reality that you have, okay, is abstract. It's inside your brain. Mine is different than Pierre's, different than Roy, different than everybody has their own. There's no objectivity whatsoever. Okay? Physicists have been trying to argue that there is, but they haven't given us the final answer yet. Right? So in fact, they got into the point where not only they cannot make veridical claims, they cannot even make falsifiable claims, talk about strings and so on. So what I say about the physical world that we all share is exactly the same I can say about pi. It's an abstract concept that has potentially an infinite efflux. We're going to be able to generate infinitely many measurements from now to infinity. Okay? But we have a finite representation of it, which we can use to make predictions, to measure discrepancy. Okay? It's exactly the same thing. Okay? It may seem a bit weird and fishy. Can I show you? Okay. So these abstract concepts are manifested through sensors and represented subjectively. They generate percepts. We can hallucinate. You know, you can predict what the next decimal of pi would be. And if now I show you something which is not, well, now you know that it was off. So are the laws of physics. What are the laws of physics? The laws of physics are an algebraic language. So it's a human artificial language that expresses relations among, not data. Okay, the laws of physics, let's take Newtonian physics, right? F is equal to ma, it's not a relation between a force that you measure, a mass that you measure, an acceleration that you measure. Whatever you measure, you plug them into F minus ma, you'd never get 0, ever, right? So it's just an abstraction. It's a relation between abstract quantities, F, a force if I could measure it with infinite precision, which you can't, and mass if I could measure, you can't. This is a completely abstract concept, okay? Does not exist in reality. What we can do is we have internal representation, we can hallucinate data, we can map data, so we can falsify, okay? So in a sense, what Kundering advocated, which is the subjective or the Cartesian account of perception, as far as I can see today, is the only defensible one from a scientific standpoint, even though it's the one that is considered the least scientific because it's entirely subjective. Okay, so what are claims that we can make today? One, bad news, any feed-forward architecture, no matter how big, no matter how many parameters, no matter how big the data set you train it on, can never understand, in the sense that you understand pi, okay, can never understand any abstract concept or real concept, right, besides what are called topologically trivial concepts or tame concepts. For example, the concept of even and odd number, which seems trivial to you, is actually not trivial. So a deep neural network cannot classify even number from odd numbers. Okay? Not a multilayer perceptron, not a convolutional network. Okay? A transformer can. Okay? And an RNN can. So the corollary is that convolutional neural networks cannot learn abstract concepts beyond trivial ones, which are finite partition of data space into a finite union of topological complexes. Okay, so for instance, they cannot tell even from odd beyond a certain length of the digit. Okay, nerves, if you're familiar with this, nerves are a multilayer perceptron trained with a collection of different posed images taken of a physical space, and you can use them to interpolate. But you really have no understanding of reality as the abstract concept of physical space that generated the data that you finitely sampled. Okay? It's just not possible, provably. Okay? And it's not subtle, it's just, you can't. Okay? Now, some quasi-positive answer is that a transformer or networks that have some type of recursion mechanism, whether it's a true recursion mechanism as in RNNs, or a mechanism that co-opts the data itself as a form of recursion, as in transformers, used in autoregressive way, they can encode abstract concepts. So you can do it. You can design a transformer that, for instance, encodes square root of 2, which is an abstract concept. What we don't know is that even if it can represent it, it's not clear that it can learn it from data. Okay? For instance, you learn pi because some teacher in elementary school explained the concept to you, but if I were trying to teach you pi by showing you 3.141568, blah, 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 at some point, is there a finite point in time when your brain would go, I got it. From this point on, I can generate all the infinite decimals of pi, okay? Which is different than I can represent pi, okay? Can I learn that inductively, okay? So the answer to that is it can, it doesn't necessarily do that, but even when a network does it, you, an external agent, can never know when that has happened, which is exactly what happened in this experiment, right? You can understand pi, you can from finite observations, but whenever you stop, you can never know if the next digit will be right, okay? This is why when you give exams to students, right, how do you know the students understand? Well, you give them a question. If they give you the wrong answer, you for sure know you don't understand. If they give you the right answer, can you tell that they understand? No. You can just tell that they did not understand. That's most you can do, okay? So in a sense, Popper was right from this perspective. So we can falsify, okay? So some conclusions here is that, so does that make sense to you? Do you see how this connects with a little experiment we did? Okay, but you can prove these things, okay? So, so what we can do with these models is we can, if we catch them making mistakes, then we know they are not getting it. They don't get it. They don't have it, okay? But, you know, maybe with more data, more time, and so on and so forth, they could get it, and you can prove they could. You just don't know when that happens, okay? So, a few practical conclusions here. So Shannon does not really convey any semantic notion, which is not his fault. That's by design. He didn't care about that, just transmission. Fisher, the lowly Fisher information, does actually capture very important aspects of generalization and knowledge. And we can measure these quantities for real networks. And there are interesting issues in the training dynamics that I will not get into. It's an interesting topic where things that happen during learning happen very early on. There are also practical procedures that you can put in place to limit the amount of accessible information in a network, for instance, for privacy reasons. And also, there are topological structures that you can put in the space of learning tasks to measure how different or how far tasks are from each other. As I argued earlier, that we are at this point where we have won the imitation game. So from this perspective, Turing's point of view is over. If all you need to do is to be able to synthesize realistic data, we're already there. Okay. Now, can we know whether, in this case, you know, the Midjourney, the diffusion model gets reality? Well, we know it doesn't right now, because we know that in the real world, people don't have 3 legs or 7 fingers, or, you know, so we know it's not there yet, but there's no reason why it couldn't get there. Okay. Now, I've talked about language as an inner language of, you know, people that do language think of natural language, human language, but, you know, cats have language, cats reason, quite sophisticatedly, I might say. Dogs have language, that was proven by Gary Larson. Certainly language is not a human faculty, right? Wherever there is some form of symbolization, abstraction, as well as relation process. Now, once you develop an inner language, the myth that you hear is that language is born or arises out of the need to communicate. I don't buy that for a second. I think that language arises out of the need to solve complex interaction tasks with physical space. Once you have a language, then it's easy to use to communicate, because if you and I are embedded in the same physical space and we observe the same things, I can give you a signal like a sound that you can easily connect to your representation of that physical space. Now we have a symbol that's shared and we can use it to communicate. Okay. So once you have an inner language, it's easy to translate from one to the other. So can the internet reason? The internet is a closed system. You know, there's bits flowing. Can the internet reason? Can it become an autonomous system? And once you take humans out of it, yes, it can. But we will not know if and when that has happened. That's just where we are. But we can still falsify. We can still tell. We can do an experiment that will expose it and say, no, it's not reasoning. And from that perspective, not all experiments are equivalent. So vision, as a highly nonlinear modality, plays an important role. That sound, another modality that rely on linearity of energy transport phenomena, do not possess. So from that perspective, vision is fundamental. And if the digital system does develop this kind of inner representation, inner language, then it can reason. And how do you know that you are not, you know, that what you're observing is from this digital system is not real? Okay. So this is where it's still quite open, and we're still in the process of trying to figure it out. But I do work for a company that not only has a cloud where bits come back and forth, but also has an embodied arm that delivers package to your door. And so reality, in my view, is, you know, if you have bits in your bank account and at some point they go down, but something shows up at your door that is tangible, you can pick it up, you can use it. Okay, so that's proof of reality in the form of tangible assets that otherwise, if you live in the world of Zoom or Twitter, whatever it is, what you see is, you know, some manifestation of some abstract concept that lives inside the system, and you have no handle whatsoever to tell whether something is real or not. Okay, so that's kind of the philosophy of the package, if you wish, that I'm trying to pursue. And this has implication that you can probably hint at, they can probably begin to see in security, authentication, in up-level learning, and in transfer learning, and a lot of other applications that I'll be happy to elaborate offline with those of you interested. Thank you.
Thank you, Stefano. We have time for a few questions. Anyone has them?
So I have a question for the first part of your talk. And then you mentioned that you can bound the test error based on the training plus the term with the mutual information between the weights and the data. And I wonder how tight is the bound, and do you have, well, you can calculate them. I don't know if you have empirical evidence to show that once you consider the bound, that can improve the generalization.
Yeah, so the meaning of these generalization bounds is the meaning that I attribute to them is not to give you a number that tells you how well you generalize. I don't know of anyone in the practice who uses these bounds to actually measure how well the network generalizes. Not one, ever, right? Why? Because to do that, you just do cross-validation. Right? And any of these bounds, no matter the claim of they're not vacuous and blah, 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 they're not useful from that perspective. So as a number, I don't know of any of these bounds that is of any use, okay? The meaning of these bounds, as far as I'm concerned, is as a function that you can define up to a constant. It doesn't really matter what the value is, but the function is the one you should minimize because the argmean, not the value of the minimum, is what matters for you to know that you achieve maximum generalization. It doesn't tell you how good your generalization is, but it tells you you cannot do any better. Does that make sense? Okay, so, and the reason for that is because this particular quantity, the Shannon mutual information, number one, it's really not meaningfully computable. Number two, even if you can, it doesn't make any sense because it doesn't distinguish between accessible information and complexity of the coding length of the weights. Okay, so the value of these as a number that measures generalization of a particular network is 0 in my opinion. I hope I don't offend anybody working in generalization bound. We do, by the way. We have a paper in URIPS on leave one out conditional mutual information bounds. So we are trying to get numbers, but out of, in the sense of trying to develop tools that allow us to define these concepts, not so much because we use these numbers to actually predict generalization.
You said that at the end that entropy in the channel end A doesn't encode semantics in any way, but from empirical evidence we see that larger models that require more bits to store in memory, tend to be more expressive. Could you comment anything on why do you think like larger models are better than smaller models?
Yeah, so you said a few things there. I did say that channel entropy encodes meaning. It does not encode meaning, right? So there's one question there. There's one question about expressivity, and then there's one question about working better. And these are three different concepts, so I'm going to try to unpack them. So from the first one, information is not the same thing as meaning, right? So information is complexity of the data that is usable by the network. Now, how you use that information is a subsequent step, and in order to attribute meaning to the information that comes from the data, you need a language of some sort. Now, either that language is imposed by the system or by the operator or by data or by the environment, in which case that is the meaning, right? When you train a language model, the meaning is the meaning of the text that you train with, okay? Now, the alternative, which may still be possible even for language models, is that the network itself develops an internal representation that is tokenized, that has symbols and has relations among symbols, right? So, so that's one thing. So in terms of over-parameterization and generalization, you're probably familiar with these claims about, deep network requires rethinking generalization because you have the bias-bias trade-off, and it would seem like these massive parameterized networks should not, should overfit, but they don't, and so why is that? Well, I think there's a straw person argument there, because in the bias-bias dilemma, what trades off, the complexity used to trade off is not dimension, but it's information. Okay, dimension is an upper bound of information. And so if you do the bias variance, not in terms of dimension of the weight space of these networks, but information they contain, then bias variance is perfectly satisfied. And this notion of information does satisfy that. So, okay, so from that perspective, there's no require rethinking anything. Okay, so the bias variance applies, you just need to use the right measure of complexity. Okay, which is not size of the weight space or dimension of the weight space. Now, with respect to these super large networks, there are emergent behaviors they exhibit in terms of transferability that are empirically evident, which is why people are suggesting that these networks do develop an internal language, because you can use them to answer query or to deduce answers to queries that were not manifest in the language that's used for training. Right? So I do not know how that happens. Okay, I wish I did. I don't know anybody who understand that, or if they understand, they've happened to explain it to the world, to me. It's a fascinating question, and I think it's the question that we're trying to go after here. So there are certainly things that are happening that we don't understand. It's a fascinating area, and I hope somebody comes along that can explain it in ways that I understand it.
Hi, Stefano. In terms of learning physical laws, I don't have exactly the mental picture of what, like for example, learning some sort of relationship